Hi, in this video I'm going to make a walkthrough of this MATLAB example called train network with multiple outputs. In this example, we're going to make a network to detect digits in images and also to detect their corresponding angles. What we're going to learn in this example is how to make a network with multiple outputs, how to train a network using a custom train loop, and how to use the dlfeval and DLARRAY combination to do this custom training loop. Okay, so let's get to the example. Okay, as any deep learning problem, we have to get the data first, although in this case we're gonna get it very easily with this. It is already pre-processed. So in here we're gonna get an array of, actually we get a tensor of images. This is an image 28 by 28, it's grayscale, and we have 5,000 samples. And these are going to be the corresponding 5,000 samples, indicating the number of the digit is 0 to 9. And the final one is going to be the angle, which is also 5,000. Okay, so the angles should be maybe between negative 45 and 45. Okay, so it's 5,000 samples as well. So we're going to create data stores for them. In here, we're going to specify the iteration dimension is the fourth one, where that's the dimension of the sample. And in here, we just create data stores. Okay, but that's not it. We have to combine them because to be able to use the network to provide the input data and the expected values. And usually we see only two in here for the input and the expected value, but since we have multiple outputs, we specify a couple of them. Okay, so that's our data store. Let's pick up the categories, which are 0 to 9, and so we have 10 numerical classes and 5,000 observations. We're going to use this later. And so let's pick, just to observe the data, let's pick a random permutation of 64 elements. And we're going to use the imtile function, and what this is going to do, we pick up the 64 random images, and this imtile is going to create an image with all these 64 input image. So let's just display it. Okay, so the numbers have different angles and different styles, which is good for this type of problem. Okay, so now let's make the neural network. First, we create a set of layers, and usually these layers are sequential, and when you specify the layers like this, they're going to be connected automatically, but in this case we have an addition, so we expect a couple of inputs. So the first one is not going to be connected first. Okay, so this is a regular classical CNN input layer, expecting the size of the image, doing normalization, some convolution, 5 by 5 convolution, then using Bayes normalization, ReLU, 3 by 3 with a stride of 2 convolution. So the downsizing is going to happen in this convolution, one of the downsizings. Okay, so let's take a look at the network. Let's just see it. Okay. No, so this time is the other graph. Okay. So let's take a look. It takes a while loading. It's there already. So as mentioned before, when you put the layers in an array, it's gonna connect them sequentially, but the addition has a couple of inputs, so we have to connect the other, and yeah, we have to fix this. Okay, so we can see the sizes in here. The convolution is gonna downsize it. This convolution because of the stride of 2, and then yeah, it remains like that. Okay. So let's do the connections. First, we're gonna create another branch with convolution. This is a regular branch and regular layer, and we add them. And when we add them, they just appear in the graph. So it's like a separate word because it's not connected yet. So you can see it like this. So now we're gonna connect this ReLU one, which is this one. It's gonna be connected to this one in here, and then this ReLU skip is going to be connected to the input. Since this only has a single input, we just and and any layer can have infinite outputs. It doesn't matter. So we just put the name of the layer and these two layers, and that's enough to make the connection. But to connect this one with the addition, we have to specify the input. The first connection that was done in here for the addition, it just picked up the first one and to connect it. But now we have to specify the input like this, input 2. Okay, so let's do it. And finally, we're also going to create an additional fully connected layer, and it's going to be connected, you can see from the addition to the output, because this fully connected layer, it cannot be seen in here. But this is going to be for detecting the digit. So that's why you have a softmax, because it's for classification. This one is for detecting the angles. So it's going to be a regression problem. So it's going to be just a fully connected layer. Okay, so let's make these changes, make the connections, and then create these and connect them. And now let's take a look. So you can see the addition. And this is for the regression and the classification, and the branching and the connected to the corresponding inputs. And if you do this, still is complaining about the outputs, but that's going to be fixed later. Okay, so we connected to the second input. Okay, let's keep going. Now let's create the network, because since we're going to do a custom training loop, we need to work with DLARRAYs. And the DLARRAYs are going to, when used in combination with dlfeval, they are going to record all the operations, and that assembles a DAG, a directed acyclic graph, representing the pipeline of the network. And in addition to the operations to compute the loss, from the loss, using the gradient function from the MATLAB deep learning toolbox, is going to compute the gradient symbolically, and then it's going to compute the actual values that are going to be used to update the learnable parameters in the deep learning network. So it's important for all the computations that are done within the network and also outside of the network to use DLARRAYs. But in addition to put all the data in DLARRAYs, it has to be wrapped around also GPU arrays. The data is going to be both of them. It's going to be a DLARRAY and also a GPU array. By using the GPU array in the data, then MATLAB is going to take advantage of the GPU to speed up all the computation, which is very important. Okay, so now with this we have the deep learning network. So let's take a look at the network. Now everything is fine, no errors. Okay, good, and even has the numbers, the fully connected specs. The output is going to be one hot encoded, so it's going to be 10 elements with 0 to 1 probability of being a particular digit, and this is going to be the angle, which is a real number. Okay. Okay, so this is the network, and notice that you have the learnables. These are the weights that are going to be trained, and these are states that can be used in normalization, in batch normalization layers, and the name of the inputs and the outputs. Let's take a look at the learnables to see how they are. Okay, notice that this is going to be important part of the computation in the network, and they are all DLARRAYs, so that is good. And this is done by using this. Okay, so now let's train the network, and I created a method for that because it's kind of easier for me to debug, but you could use the live script if you prefer. Okay, to make this faster, I'm gonna just put 10 epochs. So let's run it. It's clearing here. Okay, okay, so we have the data store for training, and we want to convert it into a DLARRAY and also have a mechanism to get the batches. So we're gonna use the mini batch queue, which is a function from the deep learning toolbox. And this is going to return DLARRAYs when we read it. This is not a DLARRAY, but it's going to do that. And I understand that this is going to make also, it's going to convert them, wrap the data not only in DLARRAYs, but also in GPU arrays to speed up the computation. Okay. Okay, so let's do this again. I'm going to put a breakpoint. This is my callback that is going to do some pre-processing. So let's create it again just to see how that goes. Okay, first the data is gonna come as cell arrays by the data store. We don't want that because the neural network expects tensors. So we're gonna concatenate in the fourth dimension to convert the cell array into a tensor, and where the last dimension is gonna be the sample dimension. Okay, and the same is gonna be for the expected digit value and the expected angle. And we're gonna here we have the digit 1 by 128, but we have to convert it to a 1 hot encoding. Now we have 10 by 128. Notice that these are raw tensors, but the caller, which is the mini batch Q here, is gonna wrap them into the DLARRAYs, and that's what you're gonna get when you use the next method. This is a method from mini batch Q, so that's what we're gonna see it in a moment. Okay, so let's continue. Put a breakpoint here, remove this breakpoint. Okay, good. Okay, now this is for display purpose. We're gonna use an animated line with just the color, and what this is gonna do is that for each iteration we record the loss, because this is the loss, the training loss that we expect to go down as the training goes. This is the custom training loop that we are using dlfeval along with DLARRAYs to compute the gradient, and there's a gradient function inside of here, in the side of this callback. To complete the gradient, we get the gradients, and then we use Adam update to update the learnable parameters in the network, and then keep going. That's why it is called a custom training loop. Okay, so with this loop, we want to monitor the progress, and for that we use this animated line, and we insert points in it, and the points are the x is the iteration and the y is the loss. So notice that this is a deep learning array and a GPU array, so we have to extract the data. This is a method from the DLARRAY, and then we have to use gather, which is a method of the GPU array, and convert it to double, and that's how we get the scalar value from the loss. Okay, and this is the object that we created here to basically animate the progress. We're gonna see that in a moment. Okay, so let's create that. Okay, this is trailing average, and this is used for the adaptive momentum training algorithm. At the beginning it's empty, but then it's going to return values for them, and it's going to be fed back into the next iteration. Okay, so we're going to have 10 epochs. This is a method from the mini batch queue to shuffle the data. It's good to have data in random order. It's better for training. Okay, so now let's take the next batch from the mini batch queue. So we have a tensor for the input images, which 28 by 28 by 1 by 128. This is the digits 10 by 128, and the angles 1 by 128. But this is not regular. It's not a raw tensor as we saw in this method. We're gonna see why. This is basically, yeah, we have the numerical data, but it's a DLARRAY as we want to get the gradient computation and the custom training loop, and we have the GPU array to accelerate the computation. So that's expected, and all of them are like that. You can see here, this is a DLARRAY. Everything is like that. Okay, now let's go to the important part. Is to compute the DAG within dlfeval. Okay, the contract in the MATLAB deep learning toolbox is that if you do computations on DLARRAYs within a callback that is executed from the dlfeval, the computations are going to be recorded into a graph, into a DAG. Although you're going to see numbers, numerical values for each computation underneath, it's going to remember those computations. And then we're going to use the gradient function to symbolically determine the gradients. And at the end, you get values. And the values of the gradients are going to be here, which are going to be used to update the learnables. Okay, so let's go inside by putting a breakpoint in here, which is the callback that is used within dlfeval. Okay, so we're going to put a breakpoint here. Okay, it's going to put a breakpoint here. Just run it. Okay, so we have the batch of data in here, the 28 by 28 by 1 by 128, and yeah, this is your network. So the first step to compute is basically compute the output. So you have the input of the network, and we use the forward, which is a method from the deep learning network, and we get the expected digit category and the expected angle, and we get the state, but this is for batch normalizations. You can see here that these is the state average, the mean, the variance for the batch normalization layers, but we have to update the network with that outside of this. Okay, so the output is going to be the expected categories, expected angles. So now we take the difference between the predicted value and the expected value, and we use cross entropy function, which is a MATLAB deep learning toolbox function. The same is mean square error. A cross entropy is because this is for category, the expected digit, and this is the expected angle. It's a regression problem, so that's why we use this function. Notice that the output is going to be also a DLARRAY, and the output of this is going to be also a DLARRAY. So so basically the DAG is being assembled here. The DAG is going to go from these computations all the way to the top of the inputs of this neural network. Okay, so now we have two separate DAGs, independent, but we're going to put them together into a single loss function using this way, so we give less priority to the angles. So now what we have here, we have a scalar, but underneath there's a huge graph that includes all the convolution operations, all the pooling operations, batch normalization, everything. So in that graph, we're going to compute the gradient using the DI gradient function. Okay, so here we have the loss, which has the DAG, and then the learnables. The learnables are part of the network, are an important part of the computation of the network, so they are nodes within the graph. So whatever, if this is like having a, okay, give me the gradient, give me the dx, dy. So, sorry, opposite direction, dx, dx. So basically the y is this one and this is the x. Okay, so this is not, it's not the inputs, but it's part of, has to be part of the graph. So it's gonna do the traversal, it's gonna do the symbolic computation, and it is symbolic because I debug through this one, and if you put a DAG that contains a signs, it's going to use cosine, and if you have in the computation x to the n, it's going to use x to the n minus 1. So actually it's doing symbolic differentiation. It's not doing like a x1 minus x2, y2 minus y1 divided by x2 minus x1. It's not doing that. It's basically actually doing the symbolic. So that's why it's kind of confusing and fooling, because we see numbers, but actually there are formulas behind this, although they are not visible. Okay, so now it's going to compute the gradient symbolically, and then it's going to compute the values, and the output is also going to be a DLARRAY. You can see that the gradients are DLARRAY, and they have the same size as the learnables. So let's take a look at the learnables. You can see the size more or less, and let's take a look at the gradients. So they are the same size, and that's expected because the gradients are relative to learnables, and they're going to be used to update the learnables, and that's how you train the neural network. Okay, so let's get out of here. We already have the gradients. Okay, now that we have the gradients, we have the state, so we have to update the network with the new state, and the loss is only used for plotting the progress. But the gradients is going to use with adaptive momentum, and he knows that this is a deep learning network, so he's going to look for the learnables, and it's going to apply these gradients to the learnables. So this is the state of the algorithm. So you just pass it around the number of iterations, and you get the updated deep learning network. Okay, so it's going to plot the progress, it's going to add the points. So let's take a look at how this looks. Okay, it's gonna start with a high error. And let's see how this exploits the. Sorry for that. Okay. So yeah, so MATLAB is using a GPU at 5%. OBS Studio is taking more advantage of it. Maybe that's why MATLAB is not able to get advantage. But anyway, yeah, it went pretty fast. It's in epoch number 7. should have the iteration number in here. I'm gonna give pause because this takes a lot of time. Okay, it's finished. The loss is pretty low. That's good. So let's test the network using this here. So we have to get we get the data set from the same place, and yeah, we have to create the data store the same way that we did it. We have to use combine because we're gonna use mini batch queue, provide this data store in there, and then we are gonna make a loop to basically get a collection of the data. So we get data one batch at a time. We use the train network, pass the input image, get the predicted values, and we have to one hot decode it. The network is gonna give us an array of 10 values, so we want the number, actual number. So we're just gonna append the result of the batch. Also, we have to extract the data in here because we have a DLARRAY. We want the raw data, and then we have to decode also the test data. Has to be decoded because the test data is coming through the mini batch queue, which is gonna use this method to encode it. So we have to decode it as well, and then we just compare the expected value. In this case, well, it's basically comparing the whole batch. So we're gonna append that as well, and yeah, it's gonna compute the difference between the predicted angle and the actual angle. Okay, I'm gonna collect the result, so let's just run it. This usually is very fast. Yeah, so the accuracy is 97%, and a very plus minus 7 angles. So now let's plot it. Let's pick up 9 random images just to show them, and we are gonna use a 3x3 plot. I'm gonna put the image in one of those subplots, and we're gonna use the predicted angles, create a line, a plot. Use the plot command to put a line with that predicted angle, and also we're gonna make a line with the expected angle and just put the label on top of it. So let's do this for 9 images and see the result. Okay, so yeah, with only 10 epochs, let me see if we got an error. All the labels are predicted correctly. There's no mistake. Yep. The angle is a little bit off in here, but in here is very exact. The angle had, as we saw, plus minus 7, had a little bit trouble, but it's not that far away. Okay, so that's it for this video. Thank you very much for watching.